Okay, what we're doing is we're doing transformations. So we're going to take graphs and we're going to transform them. Can you turn around? There's no way you can see anything. Hey, move your whole desk. Okay. Transformations is a fancy way of basically just saying we're going to move the graph around. And a lot of this unit is fancy talk. So when we say things, you need to know what's actually going on, but you also need to know the math terms that's going on for it. If you look at this, the red line, and they're all black lines on yours, but the red line on mine, how did it become this black line? Right. The y-intercept, so it shifted the y-intercept down. So that's one answer, is if you look at this, you can see that it's actually just moved down 3 units. So if you pick any spot, you pick right here, which is way off. If you pick a spot right there, 1, 2, 3, it's moved 3 spots down. And if you pick any spot on that first line, you can do that. 1, 2, 3 down. That's one answer. But it's actually done 2 different things. It could have done just that, or it could have done something else. What else could have been done, Noiji? Yeah, you could have seen that it actually moved to the right. Neither answer is wrong. If you're just looking at that graph, you could have said, oh, it moved 3 to the right. 1, 2, 3. There's the new spot. 1, 2, 3. There's the new spot. Neither answer is wrong. If you're just... Pardon? Move down. So the one transformation, you could have said it moved all down, or you could have said it moved all to the right. Either answer will work. When we say we're moving things, we say they translate. So for this, we would say it translated 3 units to the right. Or we would say it translated 3 units down. In math, we can write that out. So you can actually put that into your equation and make it move 3 down, 3 to the right, stuff like that. That's what we're going to do this block. So we're going to do transformations. Oh, it's close. We're going to do transformations on how these things move around. Okay. We do quadratics in this unit. That last example, that was a linear equation, just a straight line. We do quadratics, meaning we do things with x squared. So that's what we're going to work with. Pull out your graphing calculator. Go to your y equals. Make y1 equal to x squared, and make y2 equal to x squared plus 3. And graph both things. I don't know. Just use whatever with Dawson. You'll get the same experience. So, you should have gotten 2 graphs. Your x squared graph will always look like this. That's your basic x squared graph. That's important to know. If you ever don't remember what the original graph looks like, you can just graph it yourself and look at it. But it always looks like that. It's a parabola, facing upwards, and the vertex is always at 0, 0. That's a basic x squared graph. What does your other one look like? It's the same thing, but it's just 3 up. And that's a good question, and that's what the other class said too. This Q value, notice that it's not called C. It's called Q. That's because we're about to create a new formula. So in general form, your C was your y-intercept. That's not going to be the case for us anymore. So that isn't necessarily going to be your y-intercept. But what it does do is it moves your graph up and down. So your q value, it translates your graph up or down. So if my q value was 5, what would happen to my original graph? It'd go up 5. If it was -7, it would go down 7. This is the easiest transformation to do. It's just your regular graph. You added it onto the end. It's easy to put in your calculator. It's easy to visualize. And the positive and the negatives all make sense. Positive values go up, negative values go down. Kind of makes sense. It's kind of logical. I picked 3 randomly, just to show you guys what it looks like when you do a Q value. You're right, yeah. This graph, this next slide. We're going to do this for this entire lesson. So we're going to talk about one, and then there's going to be a slide that has it explained very nice. You might want to star those slides. This one right here, this is a good slide. It's just an information slide. It's everything I just said written out nicely with nice diagrams to explain it. Diagram on the left. Notice that we have a positive 2 added on to x squared. That's why our dotted line went up 2. The next one, we have a -3, so it's x squared minus 3. Our regular graph went down 3. Easy, right? Easy. Beautiful. The next thing we're going to do is we're going to introduce a p-value. The p-value is one that we make a lot of mistakes with because it's attached directly to the x, meaning that if you add a p-value in, it's x minus p in brackets and then squared. So you'll see it right here. X minus p squared. In y1, put in x squared. In y2, put in x minus 3 squared. And then graph it. Our first graph, our x squared, is still the exact same. That's our basic standard graph. What does our x minus 3 squared look like? Which way is it? To the left. How far left? 3 to the right or to the left? 3 to the right. Did you use brackets?
I did not. Yeah.
There we go, I just gave brackets.
It's x minus 3, not x negative 3. The negative button and the minus button are different. Yes. Don't put x negative 3, put x minus 3. Okay, did everybody get to work?
Why would it fall
Okay. Everybody's got their graph now?
Yeah, we're
So what do you think your p-value did? Soccer.
How much would be left and right on
Yeah.
X?
Yeah, it translated it left or right, depending on the value. Here's the thing that's kind of messed up about your p-value. X minus 3 squared. If I ask you, what's the p-value? What's the p-value in this question? It looks like negative 3. It's positive 3. Because in our formula, it's x minus p. Yeah, don't worry about that. Dawson.
So it's an A, could it be like an infinite set of brackets?
Good question. So if I gave you x plus 3 squared, what would your p-value be? That's when your p is negative 3. So the value of it is reverse of what it looks like. Because the formula is in x minus p format. Zucker.
Is that where you why you use as your product law?
No, not quite. This is kind of a whole new thing. We're not going to use zero product law really at all.
But does it work? Because it's just whatever's the opposite.
No, no. I see what you're trying to say now, but no, yeah. Not a bad thought. Okay. Okay, so our formula, that's what matters so much. If you look at our formula right here, it's x minus p. So if we look at this right here, x minus 3 squared, and I ask you what's the p-value, the p-value is just 3 because the minus came from the formula. The minus didn't come from the p-value. Now, if I did another question where it was x plus 3, notice that the sign has switched. So my p-value must have been negative 3. Basically, know that it's always the reverse. The value is always reversed. If you see minus, it means you're moving to the right. If you see plus, it means you're moving to the left. Again, this slide explains it all beautifully. So if you're ever lost and looking for help, look back at these slides because it's detailed. This is the hardest one. Your A value. So y equals ax squared. It's the slide we're on right now. We need to figure out what A does. So what I'm going to ask you to do, y1, x squared, y2, 3 times x squared, just like that, no brackets. 3 times x squared. Graph both of them in your calculator. I know that's going to be my basic parabola like that. You graph it and try to describe to me what the other one looks like. I'm just using 3 because I'm just trying to show an example.
So it's like a skinnier version. It's a vertical stretch.
So,
If we turn it upside down, it kind of looks like a highway with the opposite distance.
okay. If you graphed it, it looks skinnier. Right? That's what it looks like. The second graph is just the skinnier version. Skinnier doesn't fly in that. Logan.
So it's like 1 or more. It's just
Yeah, exactly. And instead of saying skinnier or fatter, we say it's been stretched by a factor. So when you see something like this, what you've really done is you haven't changed any of the x values. What you have changed is the y values. Which means, if I take a point on my original graph, and it's over here, it's 2, 2, and I wanted to stretch just that point. I said the A value is 3. What's your new point going to be? Your X value doesn't change at all. So your X is still going to be 2. So it's up here. It's still at 2, comma. And then you go A times your Y value. So you stretched it by 3, so it's 3 times 2. The Y value used to be 2. Now it's 6. So that's how you got from one point to another. And what your calculator's done is it's done that for every single point. That's why it looks like it got skinnier. It stretched it upwards. Hi. Just made it up. I just picked a point on our original graph. 2, 2 is not a point on that graph. The next slide explains it all nicely, but it has a highlighted point. And Logan said it earlier. If your A is greater than 1, A greater than 1, your graph gets skinnier. If A is less than 1, but greater than 0, it gets fatter. So if it's a decimal that's less than 1, but still positive, so like 0.5, it would get fatter. If it's negative, you've actually done what we call a reflection. And it reflects over the x-axis, and all your y values become negative. So
when it's a negative, is it only to a certain point, or is it exactly
the same? So what you would do if you had a negative 1 is you would flip the entire thing over and then stretch it. So if it was like -4, you'd flip the graph and then make it skinnier. It'd just be going down instead of up.
You just times with your previous value.
Exactly. So if you had a y of 1, you times it by 4, but now it's a -4. That's why it's in the negatives. Any questions? Okay. This slide shows you negatives. We call that a reflection. So you have 3 types of transformations. You have translations, you have stretches, and you have reflections. Those are the 3 you're going to need to know. What does Q do?
Q tells you how much on the box.
It moves it up or down. Q moves up and down. What does P do? Left and right. What does A do? It reflects it, and we don't call it fat or skinny, we call it stretching. It doesn't matter, both are a stretch. So if it gets skinnier, you've stretched it by a bigger than 1 number. If it gets fatter, you've stretched by a less than 1 number. This graph has, or this slide, has our entire formula together, right here. I'm not going to give you that on the test. I'm just going to expect you to know it. We call it standard form. General form was this. That was general. Now we do standard form. Standard form is this one. I'm taking my time on this because you have to have this down, or you're going to be lost the rest of the unit. So if you don't get this stuff nailed down, we're going to be in a bit of trouble moving forward. So is there any questions about any of these things? Dante?
How do we find values to?
That's a good question. So, if we look at this, right? And there's no numbers on here right now. But on a graph there would be numbers, right? There's always grids on a graph. So we could say that this point is really 4, right? We could say this point over here is actually 2. What they could say, how has this graph been transformed? Right? It moved 4 to the right, and it moved 2 up. Because that's where our vertex was. Right? It went from 0, 0, all the way up here. So what would your p-value be? If it moved 4 to the right, what would my p-value be? It'd be positive 4. In the equation, it would be x minus 4. But your p-value would be 4. What would your q-value be? 0 would mean it hasn't moved up or down at all.
So like 2.
It'd be 2 because it went 2 up. And there was no stretch, so your a value would just be 1. If there's no stretch, your a value is 1.
You're always, so even if it's a big stretch, it's always.
Yeah, so if there's no stretch, a value is 1.
Oh.
That's if there's no stretch. Your vertex always gives away what your p and your q are. We use our vertex to find our p and q because you can't stretch your vertex. It's not possible because your vertex is 0, 0. Anything times 0 is 0. So you can't multiply it by anything. You can't stretch your vertex. Which means if you know what your vertex is, you know what your p and your q are. The x value is your p, the q value, or the y value is your q. The vertex gives away p and q. It says it right here, you can see it. Vertex is at p comma q. So that's how you're going to get numbers in the future. Tomorrow we're doing a lot of that. A lot of it. Any other questions about this lesson? Now's a good time to ask. Yeah, Zucker.
Basically, if you're moving, say, 3 to the right, you don't worry about it negative, just put it where it is.
Exactly. The negative's already there, don't sweat it. 3 to the right, that's your p-value, is 3. Now if you went to the left, your p would be negative, so it would be like minus negative 3, which would make it a positive. It just looks weird in this format. Right. It's really tricky. It's going to take practice. That's okay. And tomorrow we're going to do a lot of questions with this stuff. Any other questions?